Hey there and welcome. Ever wonder what gives a lemon that super sour kick? Or why soap feels kinda slippery in your hands? Well, the secret lies with three huge players in the chemical world: acids, bases, and salts. And trust me, these aren't just things you find in a science lab, they are literally everywhere. In your food, around your house, and even inside your body. So let's dive in and really get to know them.
So here's our game plan. First up, we're going to meet our main characters, acids and bases. Then, we'll dig into the cool theories that explain why they act the way they do, and you'll learn how chemists measure their power. After that, we'll see what happens when they meet. And then, the best part, we're going to step into a virtual lab and create two totally different salts, right from scratch.
So really, think about it. Why is a lemon sour? Why does baking soda have that bitter taste? It all comes down to the chemistry we're about to unpack. This is chemistry you can actually taste.
Okay, let's properly introduce our two main characters. In one corner, we have acids, and in the other, we have bases. They're basically chemical opposites, and the story of how they interact, it's pretty much fundamental to all of chemistry.
You know, on a really simple level, we can tell them apart just by how they look and feel. Acids, like the citric acid in lemon juice or the acetic acid in vinegar, they have that classic sour taste. Bases, on the other hand, tend to be bitter and feel slippery or soapy to the touch. And of course, there's the classic litmus test from chemistry class. Acids turn blue litmus paper red, while bases turn red litmus paper blue. It's a neat little chemical trick.
But what's really going on at the molecular level? Well, think of an acid as something that loves to give things away, specifically protons. When you dissolve an acid in water, it literally donates a positively charged hydrogen ion, which is just a proton, to a water molecule. That water molecule then becomes what's called a hydronium ion, or H3O+. This little guy is the true signature of an acid doing its thing.
Now, on the flip side, we've got bases. And there's a special type of base called an alkali. An alkali is just a base that happens to dissolve in water. When it does, it produces negatively charged hydroxyl ions. That's the OH you see there. The easiest way to think about it is like this. All alkalis are bases, but not all bases are alkalis. Kind of like how all squares are rectangles, but not all rectangles are squares. It's an important little distinction.
Okay, so now we know what they are, but let's figure out how they work. Our understanding of these guys didn't just pop up overnight, you know. It evolved through some really clever scientific theories. So let's see how those ideas explain their behavior and, maybe more importantly, their strength.
So yeah, our understanding has definitely leveled up over time. The first big idea, the Arrhenius theory, was pretty simple. It said acids release H+ ions in water and bases release OH- ions. But a newer, more powerful idea came along, the Lowry-Bronsted theory. It says an acid is anything that donates a proton, and a base is anything that accepts a proton. This is a way broader definition, and it works even when you're not in water.
And this diagram here shows that Lowry-Bronsted theory in action, and it's just perfect. Look closely. You can see the acid molecule on the left ready to give up its proton. The water molecule, which is actually acting like a base here, swoops in and grabs that proton. And what's the result? The acid is left behind and the water has transformed into that hydronium ion we talked about, the H3O+. It's like a perfectly choreographed chemical dance.
But here's a key thing. Not all acids and bases are created equal. Their strength all depends on how well they break apart, or dissociate, in water. A strong acid is like a fully open fire hose. It just blasts almost all of its protons into the solution at once. A weak acid, though, is more like a slowly dripping tap, releasing its protons just a little bit at a time. And the exact same idea applies to bases.
Okay, so if we've got this whole range of strengths, how in the world do we measure it? Well, for that, chemists have a really elegant tool, the pH scale. The pH scale is our go-to ruler, and it runs from 0 all the way to 14. Dead center, at pH 7, you've got perfect neutrality. Think pure water. As you go down towards 0, things get way more acidic, and as you go up towards 14, they get more and more alkaline, or basic. And get this, it's a logarithmic scale, which means every single step is a 10-fold change in acidity. And a universal indicator gives us this awesome rainbow of colors to map it all out visually.
Now, while that universal indicator is great for a general idea, sometimes chemists need to be way more precise. And that's where these specific indicators come in. Each one is designed to change color at a very specific pH. Take phenolphthalein, for example. It's totally colorless in an acid, but the second the pH turns even slightly alkaline, bam! It turns this brilliant, vibrant pink. It's perfect for knowing the exact moment a reaction is finished.
So we've got our two main players, the acid and the base. What do you think happens when they finally meet? Well, this is where our third character finally steps onto the stage, the salt.
When an acid and a base react, they basically do a partner swap. The base gives a metal ion over to the acid, and in return, it takes the acid's hydrogen. This whole process is called a neutralization reaction, and it forms water and a salt. The most famous one, of course, is regular table salt, sodium chloride, which is born when hydrochloric acid and sodium hydroxide face off.
And let me tell you, the salt family is enormous. When an acid and a base perfectly cancel each other out, you get what's called a normal salt. But sometimes the reaction doesn't go all the way. If a little bit of the acid's hydrogen is left over, you get an acid salt. If a piece of the base is left, you get a basic salt. And then you get into all these other cool types like double salts and complex salts. The main point is, a salt is a way bigger category than just the stuff you put on your fries.
All right, that's enough theory for now. It's time to head into the lab. Let's see how chemists actually make this stuff. First on our list, we're going to prepare iron 3 chloride.
So this is the exact setup you'd use in a lab. The whole goal here is to combine iron and chlorine gas directly. Let's trace the path of the chlorine. It gets generated over on the left, then it's piped into this central glass tube. Inside that tube, we have our iron coil, just waiting. As the reaction happens, the new stuff that's made travels out the right side and collects in that flask. Every single piece of glass has a critical job to do.
Okay, the process itself is 3 simple steps. First, you flush the whole tube with dry chlorine gas to get all the air out. Second, you gently heat the iron coil to get the reaction going. And here's the really cool part. The reaction is exothermic, meaning it creates its own heat. So much heat, in fact, that the iron starts glowing red hot all by itself. Third, the iron 3 chloride that forms is volatile, so it turns into a gas, flows down into the cool collection flask, and then condenses back into solid brownish-black crystals. And just like that, you've made a salt from its raw elements.
But here's the thing in chemistry. You can't make every salt the same way. So for our next one, the beautiful blue crystals of copper 2 sulfate, we need a completely different method.
This time, we're going to use our old friend, neutralization. We're going to react sulfuric acid with an insoluble base, copper 2 oxide. And because we aren't dealing with any crazy gases, look how much simpler the setup is. All we really need is a beaker for the reaction, a funnel to filter out the gunk, and an evaporating dish to grow our crystals.
So, here's our 4-step recipe. Step 1. Warm up some sulfuric acid and keep adding the black copper oxide powder until it just won't dissolve anymore. That's the signal that all the acid has been used up. Step 2. Filter the hot mixture to get rid of all that leftover black powder. Step 3. Gently heat the blue liquid that's left, the filtrate, to boil off some of the water and concentrate it. And finally, Step 4. Just let that solution cool down nice and slow. As it does, these amazing, vibrant blue crystals of copper 2nd sulfate will magically appear.
And that really brings us right back to where we started, doesn't it? We went from the simple taste of a lemon all the way to precisely creating brand new substances in a lab. It just goes to show you how this fundamental dance between acids and bases is what creates the huge, amazing world of chemicals all around us.
So I'll leave you with one final thought to chew on. We saw a neutralization reaction happen in a beaker. But think about this. Your stomach is full of strong acid. If you take an antacid, which is a base, what common, salt-forming neutralization reaction is happening inside you right now? Something to think about. Thanks so much for joining me.